And now that we've got a way of dealing with continuous distributions, how do we find the expected value and the variance, those two pieces of information we're interested in? Now, our random variable is continuous, so x is some continuous random variable. Whereas when it was discrete, we said it was the sum of xpx, or we could think of it the sum of all those rectangles. But what we're now saying is, well, we're going to use the integral for continuous. It's very much the same as with integration, because that's what we're doing. Remember, originally we said, oh, we'll estimate with the rectangles, but then we said, oh, but as that approaches zero, that's going to be exactly the same as the integral. That's what we're doing here. Instead of summing up the rectangles, we're saying it's the integration from minus infinity to infinity of x px, but now it's the probability density function, so function x dx. And it's still the same value as the mean, all that sort of stuff is the same. Here is our probability density function. This particular one is just for x is greater than or equal to 16. Now we're going to model the quarterly salary measured in thousands of dollars to salespeople in this company. First of all, we'll look at the median, and we saw how to do that in the previous one, and the mean. We describe our distribution. Median will go from minus infinity, although this one starts at 16, so we'll go from 16 to m, that's what we want to find, of our function, x to the negative 7 on 2, add 1 to the power over the power, subbing in, and we get 21.112, but that was in thousands of dollars. So the median quarterly salary is $21,112. Let's now find the average, which is the same value as the expected value. So it's x times that function. Index laws, we're now integrating x to the power of minus 5 on 2, add 1 to the power over the power, and of course for this one we're going to infinity. We're using our limits. Well, our function is x to the minus 3 on 2, so we've got that backwards exponential. We know as x is approaching infinity that would be 0. Now we'll just get an answer of 26.667. So there's the mean, 26,000 odd, and the median is 21,000 odd. So what does that tell us about the distribution? We've got something that's positively skewed because the median is less than the mean. So more than half of the data is below the mean. So we must have a positively skewed set of data. Variance. Well, again, it's still the same idea. So we'll find the expected value of x squared minus the expected value of x squared. And expected value of x squared, well, when it was discrete, we said the sum of x squared px, but now it's just going to be the integral of x squared times the probability density function, function x. Let's find the standard deviation of the salaries. The expected value of x squared, so that's x squared times x to the minus 7 on 2, minus the expected value of x, which we just worked out, 80 on 3, squared. Subbing in, and we have the variance. They want the standard deviation, which is the square root of the variance. So we're 23.851, so $23,851. Now remember, what we should find is, as the standard deviation gets smaller and smaller, then we know the data is going to get tighter and tighter around the mean. That's the actual graph of our salaries there, the distribution. And you can see it very much is positively skewed. Look at all this side of the mean. And I suppose in companies that tends to happen. The workers, there's a lot of them down here getting low salaries, and then you get the few up the top here, the CEOs and all that, they're getting the higher salaries. So that's sort of the thing you would expect, I guess, if you're looking overall in the company with the salaries. So we'll add 16C to our list of exercises to look at.